Okay, this is going to be our third video in our electric flux and Gauss's law series. And so in this video, we're gonna kind of wrap up our discussion of electric flux, and then we're gonna kind of use it to motivate our generation of Gauss's law. And then from there on, we're not going to talk too much about electric flux. We're mostly going to talk about it in the context of Gauss's law because that's its sort of most useful application. Okay. So before I get started, I wanted to mention that the SI units for electric flux are Newton meters squared per Coulomb. You're not really going to usually calculate flux too much. I mean, you may be asked to, so it's useful to know what the units you're looking for are. But generally speaking, like I said, you're not going to calculate an electric flux, and we'll sort of see why that is in a little bit here. Okay, so I think this might be a bit of a long video. I'm not sure if I'm going to cut it into two parts, but we'll get rolling here and we'll see how it works out. Okay, so if we recall from the last video, for a point charge inside of a spherical shell, well, we recalled in the last video that we already knew what the electric field of a point charge would be. So we have our equation 1 here. So this is our equation for the magnitude of our electric field of our point charge at some distance, big R squared. So if we surround this point charge in a closed spherical surface of area 4 pi r squared, right? So this is the surface area of a spherical our enclosing spherical shell. We saw that we get an electric flux given by the expression that we see here, right? And so this is all from last video, okay? And we noted in last video that that this result was R independent. So it doesn't matter how large our enclosing spherical shell is, we still get the same flux, right? And we can think of that sort of by just thinking about our point charge, and then here I'm just going to draw a circle, but this is supposed to be a spherical shell. This is like a slice of our spherical shell. So the electric flux going through this surface, we can imagine, maybe I should draw these a little bit longer, but we can imagine all the electric flux sort of going through the spherical shell. If I drew a larger spherical shell, again in cross section, it would still be the same amount of flux going out, right? It's always going to be the same amount no matter how large I draw this spherical shell. It's just going to be less per unit area, but we have more area, right? So in the end, the whole thing works out, and we found that this result is in fact R independent, right? So that was a result from last video. Now, the textbook kind of spends a good chunk of section, what is it, 22.3, I think, talking about how to extend this idea from a spherical shell to any sort of non-spherical, irregular shaped enclosing surface, right? Any sort of closed surface that's going to enclose our charge. And so I'm not going to go into that whole discussion. I'm just going to write it down here. For anybody that's interested in how the discussion would go, I encourage you to read section 22.3. But really the result is all that we're going to be very interested in. And that result is what we see here. Okay, so what is this doing? This is really extending this idea, and maybe I'll just draw it on this up here. I should have probably left myself some more space. Let me clean this up a little bit and then just redraw on this. So let's imagine that these are our electric field lines. Continue out further, and in cross section, instead of a sphere, let's say we had like I don't know, some sort of weird kidney shaped thing. Okay, so again, all these electric field lines eventually pierce through our weird shaped closed surface, and again we end up with the same amount of electric flux emerging from this region, right? And even though again it may be that not everywhere our electric field is parallel to our area vector, it doesn't matter. In the end, if you add it all up, and this is what the sort of discussion in the textbook goes through, you end up with the same result. And so now we have this result, and maybe I'll talk about it a little bit more because we have some new symbols here. This symbol here, this integral with a circle in the middle of it, is just telling us that we're looking at an integral over any closed surface. Okay, so if we think back to the definition of a closed surface is any surface that cuts off some region of some volume of space, right? And so any closed surface can be represented by this integral. We're integrating over whatever that closed surface is, and this is telling us that the electric flux is equal to the integral over whatever the closed surface we want to use is of E dot dA, and this is equal to our enclosed Q, our charge which is inside that surface, over epsilon naught. Okay, and so the real sort of expansion to what we did before is that now we can deal with any closed surface. This doesn't have to be a spherical enclosing surface. This can be any closed surface of whatever shape we like, as long as it's a closed surface. Okay. We can also sort of extend this idea to closed surfaces that don't contain any charge, right? If we're surrounding some region of space that has no charge in it, our Q would become 0, and so this last term would become 0, and again we have the same expression. In this case, we would simply have no electric field generated by this Q, right? And so this term would be 0, and so everything would be equal to 0, as it would have to be, right? But there's no net electric flux. There's no net electric field from this charge, because there is no charge, right? And so we might wonder, well, what about electric field from other sources, or well, like we saw this example. We saw that example of a plane, right? That charged plane, and then we saw a rectangular box sitting in front of that charged plane. And my drawing here is going to be not the greatest, but you can imagine. And we saw the electric field lines emerging and cutting into the box and coming out. And again, because there's no enclosed charge, we have no net electric flux, and the electric field generated by the no charge is 0, so we end up with 0, 0, and 0, and the whole thing works out, right? And this is true for an irregular shape too. If we had some weird, I don't know, like kidney-shaped region here or something, the same thing would be true. We'd have electric field lines coming in, electric field lines going out, but they would all cancel out, and we would end up with no net flux, no enclosed charge, and so no electric field due to that enclosed charge. Okay, and because this drawing is so terrible, I'll probably just get rid of it, and we'll move on. This is not going to be useful for the notes here. Okay, so let's keep moving forward. So now that we have this kind of idea, this idea of the electric flux being related to this integral and the enclosed charge, and where there is no enclosed charge, the same thing holding up, except that our Q is now 0. We're now right on the doorstep of building Gauss's law. Okay, and the only thing left to consider is what if there are multiple enclosed charges, right? And to do this, we're just going to invoke this idea of the principle of superposition that we talked about before, right? Remember in chapter 21, we said that, well, we started off by calculating the electric field for a single point charge, and then we said, well, what if we had multiple point charges? And the principle of superposition tells us that we can just add up all the contributions from all those different point charges to get the electric field at a certain point in space from each of those point charges. But if we add it all up, we get the electric field at that point anyway, right? So we can add up all of our Q's, and we can calculate E at some point in space. If we use that idea on this expression number 4 that we have here, then we end up with what we see here. So we end up with the electric flux through our surface here is going to be equal to the integral over the closed surface S, which I've called S here. This S that I've used in both of these cases just signifies that I'm talking about some surface that I'm going to call S. Okay, this could be, this could be whatever, but we'll sort of see how we use this in the upcoming examples. But basically what we're saying is that the electric flux through that surface is equal to the integral over this closed surface of E dot dA, okay? And that's equal to Q enclosed, and Q enclosed here is the sum of all of the point charges inside, but it doesn't just have to be point charges. This could be some charge distribution that isn't necessarily made up of point charges. In the end, we can think of it as a collection of point charges because we can integrate over it. So it can be an infinite collection of infinitesimal little point charges, right? But in the end, this is any enclosed charge, be it a point charge, many point charges, or some charge distribution over our epsilon naught here, which I call our vacuum permittivity. The textbook sometimes calls our electric constant, right? And this boxed off equation, this is Gauss's law. This is what we're going to use. This is the real takeaway message from this chapter, really. And so the textbook does a nice job of rewriting it in a few useful different ways. So I've copied that into here. We have our electric flux on the left, and then on the second to rightmost equation is the way that I think of it. So I kind of memorize it as what's boxed in here, which gives us this first term and then the last two of the equality here. But we also have these other two, which can be useful. So we can remember that we can turn our dot product, given the right circumstances, we can turn our dot product into this this equation here, just E cos phi, which is the angle between E and A, or dA, I guess, times dA, and then we're doing the integral. Or we can think of it as the component of E that points perpendicular to the surface, right? So that's parallel to our normal vector to the surface. So these are just a few useful ways to sort of remember Gauss's law, and we're going to see applications of it coming up here in this video, hopefully, unless I decide to split it into two videos. Okay, so the textbook finishes off section 22.3 with this conceptual example 22.4. So let's take a look at that. So what do we have here? We have a dipole. We have our positive and negative charge. And we enclose it in a number of different Gaussian surfaces. And so I just used a term Gaussian surface. When we're talking about Gauss's law, we kind of use the word Gaussian surface to mean our closed surface. So a Gaussian surface is just a closed surface that we're using in Gauss's law. Okay, so if I say Gaussian surface, I just mean closed surface. Okay, so we have our dipole. Different parts of it are enclosed or not enclosed by different Gaussian surfaces, and we're asked to find the flux through or the net flux, electric flux through a number of these closed surfaces. So let's take a look at what's going on here. We've got our positive charge over here. We've got our negative charge over here, and we've enclosed our positive charge in this Gaussian surface A. And we're asked to see what the net charge, what the electric flux through that closed surface is going to be, what the net electric flux is. Well, we know that from Gauss's law, we know that this is true, right? So whatever our surface is here, E dot dA, and this is equal to Q enclosed over epsilon naught, right? And so we're looking for the electric flux. But in every case, we can just look at, well, I mean, we could look at either case. We could look at the integral that we would have to do. But if we wanted to try to do this integral over this enclosing surface A, it would be pretty difficult because our electric field is not uniform. We have it, the electric field is much stronger here toward the dipole partner here, towards our negative charge, and a lot weaker on the opposite side. So this would be a very complicated integral to try to do. You'd have to do a sort of 3D integral with a non-constant electric field. It would be a nightmare. But luckily we have this second equality, and so we know that the electric flux through this thing is just going to be equal to the enclosed charge over our vacuum permittivity, and that's very simple. That's just going to be, so basically we're going to end up with the electric flux through A is just going to be equal to, well, what's the enclosed charge? It's just Q over epsilon naught. And that's the answer for surface for our Gaussian surface A. Okay, for surface B, well, this one's enclosing the negative charge, and we can do the same trick, except in this. Oops, and that's going to be a B. Except in this case, it's a negative charge being enclosed, and so we just end up with this answer, right? For surface C, I mean, again, we could try to do the integral. We could use this term here, right? But the electric field is very messy. It's pointing out at some points, in at others. We would have to find some sort of expression to describe that, and then integrate over this weird shape. That would be a total nightmare. And so we don't want to do that. But again, we have this nice expression, Q enclosed over epsilon naught. Well, what's our total enclosed charge? Well, we have a plus Q and a minus Q, so the net charge is 0. So there's our answer. Our net electric flux through C is 0, right? There is no net enclosed charge, and so there is no net electric flux. Okay. And so what about our region D here? Our region D is this little yellow, I don't know, like boomerang shaped thing. And again, same trick. There is no enclosed charge, no enclosed charge of any kind, net or otherwise. And so the answer is very simple. Our electric flux is again going to be 0. Okay, and so that's sort of just a quick conceptual wrap up of how we should think about this flux, and a really easy way to apply Gauss's rule or Gauss's law here. Okay, I'll maybe make a note here. I'm often going to abbreviate Gauss's law with just a GL circled, so you know that if I write down GL circled, something like this, GL circled, and I say it implies this, well, I'm just talking about Gauss's law. Okay. Okay, so let's move on. And now we're moving into section 22.4 of the textbook. And so before I jump into applications of Gauss's law, which is what we're going to be looking at here, and when we do get into it, we're going to be sort of recalculating a number of old results that we got and some new ones. But before we get into that, there's a discussion from chapter 21, which is shown in chapter 21.4 or section 21.4. Where they talk about electric fields inside of a conductor in equilibrium. And I skipped over that discussion on purpose because I think it pairs well with what they talk about at the beginning of chapter or section 22.4 here. And so we're going to sort of talk about these two theorems that are going to lead us to a result that we can use going forward. Okay. And so what they talk about at the end of or at some point in section 21.4 is that there can be no electric field inside of a conductor in equilibrium. So let's just unpack that sort of mentally really quickly here. There can be no electric field, so there's no electric field inside a conductor that is in equilibrium. So what do we mean by equilibrium? Well, we mean by there's nothing happening. There's no charges moving in this conductor. So if there's no charges moving, there can be no electric field inside the conductor. Okay. Now, why is that? Because if there was an electric field inside the conductor, it would exert a force on any free charge in that conductor. Okay? And if there's a free charge inside a conductor with a force being exerted on it, because we're in a conductor, this free charge is free to move. But if the charge is moving, then we're not in equilibrium. And so because of this, there can be no electric charge, there can be no electric field inside a conductor which is in equilibrium. Okay? So this is theorem number one, and this is the theorem, and this is kind of the argument that backs up that theorem. Okay, so let's just say it one last time. There can be no electric field inside a conductor in equilibrium. Okay, so that's theorem one, and then theorem two. There's no net charge inside a conductor in equilibrium. Okay, so there's no. This is very similar to theorem one, but it is different because there is no net charge inside a conductor in equilibrium. Okay? And so why is that? We can see this because if we apply theorem one and Gauss's law, then it kind of just follows from this, right? Imagine that, and I'm going to scroll down here. This is a graphic that we'll look at in a second. But imagine that we had I don't know, some sort of a shape like this. This could be like an iron kidney bean or potato or something, right? And imagine that there was a free charge inside our potato here. And this thing is iron, right? So this thing can have no electric field inside it by theorem one. But I could draw a Gaussian surface. This is supposed to be a 3D sphere, but I'm just going to draw it in cross-section. So I could draw some kind of tiny Gaussian surface around this charge. But then Gauss's law would tell me that if I have an enclosing Gaussian surface here, if I have a Gaussian surface around some sort of a charge, then the electric field is determined by Gauss's law at that surface. So I would have some non-zero electric field inside our iron potato here. But we already said in Theorem 1 there can be no electric field inside a conductor in equilibrium. So no matter where I put this charge, I can always draw a Gaussian surface around it, which would mean that I have some electric charge. So it must mean that there can be no free charge, no free net charge inside our conductor, because we cannot draw a Gaussian surface around it, because that would lead to an electric field, and that would violate Theorem 1. Okay, so if we take both of these ideas together, we take this Theorem 1 and this Theorem 2 together, then we know that if there is some net charge on a conductor, and that conductor is in equilibrium, the net charge has to reside on the surface of the conductor. Okay, and this is the sort of takeaway message from these two theorems here. If you have some sort of conducting material, like we have in this picture here, we have some sort of a conductor. This could be, I don't know, an iron block or something, and we have some net charge on it. There's some net positive charge on it, and this thing is in equilibrium. These charges are not whizzing around. Then where does the charge have to reside? It has to reside on the surface. Okay, and so that's an important result that we're going to want to sort of keep in mind as we go forward. Let's note that this result will hold for solid shaped conductors in equilibrium, but it doesn't say anything about cavities inside our conductor. So if we carved a cavity out of this conductor that was not a conductor, let's say it was just an air pocket in the middle of our iron rock here or whatever, we could place a charge inside that air gap, and it could be in equilibrium and still sit there. But we're going to look at that situation after. The takeaway for here is that if there is a net charge in a conductor in equilibrium, then it has to reside on the surface. Okay? And so now we're going to move on to some examples. I have 4 examples planned here. We're going to look at the electric field of a charged solid conductor. So this is some conductor that's holding, well, this is a spherical conductor, a sphere made up of some kind of conducting material that does have a net charge on it. We're going to look at the electric field inside and outside of this thing. We're then going to look at a uniformly charged sphere that is non-conducting, so it's a spherical insulator, and it'll have some net charge, right? Like a uniform charge distribution on it. We're then going to, oh, I left a bunch of space there. We're then going to look at the electric field outside of an infinite rod, which we've already looked at, but we're going to look at it using Gauss's law. And then we're going to look at the electric field outside of an infinite plane, which we also looked at, but now we're going to use Gauss's law to reproduce the same result, we hope, right? Okay, so let's get into it. And again, I'm going to pause after I do each one of these examples just to save this PDF so I don't lose everything, kind of. Okay, so let's start off. This is our first example. This is 22.5 from the text. And again, this is the electric field of a charged solid conducting sphere. Okay, so we place a total positive charge of Q on a solid conducting sphere with a radius big R. We want to find the electric field at any point inside or outside the sphere. Okay, and so this is our sphere. I'm not going to worry about this plot right away. We're going to come back. This plot really just plots our result, and we're going to see how that works out. So we're going to come back to that in a second. But for now, we look at our sphere. This is a sphere. We have some positive charge. We know the positive charge, because this thing is in equilibrium and it's conducting, the positive charge has to be sitting at the surface. Okay, and here we have some other radii drawn out. We have our sphere itself has a radius of big R, and then we're looking at it at small r equals 2 and small r equals 3 and so forth. Okay, so let's get into it here. So the first thing to note is that because of the symmetry of the problem, because we're dealing with a sphere here, it doesn't really matter how we rotate this thing. No matter which way we look at it, it's going to be spherically symmetric, right? And so our electric field always has to point radially outward, right? So no matter where we go, our electric field is going to point radially outward, okay? And that's our electric field. So that's great. that means that we don't really have to worry about the direction of our electric field anywhere. That's already solved for us. We only need to worry about its magnitude, and its direction will just always be radially outward, okay? Where it's non-zero, obviously, right? So then let's imagine that, okay, so this is our center here, our origin. Let's imagine that we start building some Gaussian surfaces around the origin, and this thing will have a radius r, small r, and it's slowly growing, right? So we're looking at it as it grows, right? So we're watching this thing. It starts off small, so we start off with little r smaller than big R, right? And so we're inside the conductor. But inside the conductor, we just talked about this, right? We just talked about how there can be no electric field inside of a conducting inside of a conductor which is in equilibrium, right? And so because of that, we know that E, the magnitude of our electric field, has to be equal to 0. Okay, or if we forgot that that's sort of a theorem that we talked about, we could use Gauss's law, and Gauss's law would tell us that this is the case, right? That we would have E dot dA is equal to Q enclosed over epsilon naught, except that our Q enclosed here, because we're smaller than R, our small r is less than big R, we haven't hit the charge yet. We know all the charge has to be on the surface, and because of that we have no enclosed charge, and so in this case this is equal to 0, and this implies that since our dA cannot be 0, this means that our E must be 0, right? This implies E equals 0, and again we end up with no electric field inside this this conducting sphere, right? So our R gets slowly larger and larger until it's small r equals big R, and at that point we kind of cross a threshold here, and we have this sort of jump discontinuity. We pick up all of the charge, and so what kind of happens at that point? Let's take a look. So at small r larger than R, and somewhere in between here where we have small r equal to R, but that's where we're going to have this jump discontinuity. So at the point where small r is larger than R, well, we're going to use Gauss's law. Gauss's law is going to tell us that our electric flux, again, is equal to the surface integral over E dot dA, and this is equal to Q enclosed over epsilon naught, except that because of the symmetry of the problem, we just talked about how our electric field is everywhere going to be pointing radially outward, but also our area vector for our Gaussian surface is always going to be pointing radially outward, right? We're building these increasing size spherical Gaussian surfaces, right? So dA is going to point in the same direction as E, and so we don't have to worry about the vector nature of this, right? So this integral really becomes the integral over the closed surface, but our E and dA no longer have to be vectors. They dot into each other and multiply perfectly. And so this ends up giving us this, right? Because our E is not dependent on any of the angles in our dA, right? It's just radially outward, and our elements of dA are always the same radius away from the center from our charge distribution here. We're going to end up with this expression here, right? And this integral, this integral over the closed surface of our sphere is just going to end up giving us the area of our Gaussian surface. Well, the area of our Gaussian surface is just going to be the surface area of the sphere. That's just going to be 4 pi r squared, right? And this is, we should definitely remember this, this is the surface area of a sphere, right? And so collecting, do I have space? Yeah. So collecting these results, what do we end up with? Well, we end up with, so I'm going to take this term from the integral, which ended up being E, maybe I should rewrite it here. So this ends up being E 4 pi r squared, right? And this is just our area. So I'm going to take this term and equate it to the right-hand term over here. So we really end up with E 4 pi r squared is equal to Q enclosed over our vacuum permittivity, right? And this is basically it, right? We're just going to divide through, and we're going to end up with the electric field. The magnitude of the electric field is going to be equal to Q enclosed over 4 pi, and I can rearrange it to look more like that of a point charge, 4 pi epsilon naught r squared, right? And so what did we regain here? Well, we regained the electric field of a point charge, right? So when our Gaussian surface is outside of the charge distribution, it looks like a point charge, and when we're inside it, there is no electric field because there is no electric field inside of a conducting material when it's in equilibrium, right? And so that's exactly what this plot up here is telling us, right? So inside, when our small r is less than big R, we have no electric field. When it's equal to big R, we have this jump discontinuity, and then as we get farther and farther away, the electric field dies off slowly, right? Dies off like 1 over r squared. And that's exactly what we see here, okay? So that is this example, and maybe I'll box this too. So inside the sphere, no electric field, the magnitude is 0, and outside we have this magnitude, which looks like the magnitude for a point charge, and it's always pointing radially outward. Okay. Let's now, or actually, let me pause for a second and save this, and then we'll look at the next example. Okay, let's keep going here. Okay, so now we're going to look at the electric field of a uniformly charged sphere. So what do we have here? We have a positive electric charge of big Q distributed uniformly through the volume of this insulating sphere of radius big R, and we want to find the magnitude of the electric field at a point P, a distance R from the center of that sphere. And we have this nice drawing here to sort of show what we're doing here, right? So we have the center of our sphere here, and our small r goes out to the edge of our purple Gaussian surface, and then our large r goes out to the edge of our charge distribution, our insulating sphere that has a uniform charge distribution over it. And then outside of that, as our r grows larger than that, we're going to be outside of this thing, right? So let's take a look at how this is going to work out. I left myself a bit more room here because I think this is going to be a bit longer, but we'll see how it goes. Okay, so the similar idea kind of applies here. We don't have to worry about the direction of the electric field because, again, we have spherical symmetry. So everywhere our electric field is going to point radially outward. Okay, same as we had for the conducting sphere. We're now going to imagine this Gaussian surface, just as we did before, growing as r gets larger. Small r, like our lowercase r, is going to get larger, and our Gaussian surface is going to grow. It's going to start off inside. It's only going to enclose some small portion of our spherical insulator with uniform charge distribution over it, and it'll grow larger and larger until it encompasses the whole distribution, and then it'll continue to grow, right? So the first thing we want to think about is our charge density, right? So we have a uniform charge distribution, so we have some charge density, and let's remember for a charged volume we use rho to signify that, and so this is our charge density. Excuse me. This is our charge density, and so how do we relate our charge density to the charge? Well, we call the charge on the whole sphere capital Q, so we know that capital Q is going to be equal to rho times the total volume. So I'm going to call this volume total. So volume total is the volume of the full spherical insulator. Okay, so maybe I can write that here. This is going to be equal to rho, and this volume is really going to be 4/3 pi capital R cubed, right? And this is just the volume of a sphere of radius big R, and it has radius big R because we're talking about the whole insulating sphere. Okay. So that is what the terms in which we can write our Q. But really, we're going to want to write our rho. We're going to need to make use of rho, and so I can write that here. Our rho is going to be equal to basically just shifting this term over is going to be equal to 3Q over 4 pi capital R cubed. Okay, we're going to make use of this in a moment. And let's keep in mind again what this is. This is our charge density over the full insulating sphere. Okay, so now as our R our lowercase r grows, our Gaussian surface is going to get larger and larger, and we're going to want to talk about the volume of our Gaussian surface. Okay, so volume of G, so I'm going to call this Vg because this is the volume of our Gaussian surface. This is going to be equal to 4/3 pi small r cubed, right? Because our Gaussian surface is going to have a changing radius. This is the radius of our Gaussian surface, and so our Vg is going to be increasing as r increases. This is going to be a useful quantity for us as well. Okay. The next thing we want to look at is what is the enclosed charge, right? Because let's keep in mind, what are we trying to find? Well, we're trying to work with Gauss's law, so we're trying to, and maybe I'll write it down here so it's not so messy. So we're trying to work with Gauss's law, okay? And Gauss's law tells us that our electric flux is equal to the integral over the closed surface E dot dA, which is equal to our enclosed charge over epsilon naught, right? So the easiest way to get at what we're sort of looking for here is to start off by looking at what Q enclosed is. But our Q enclosed is changing the whole time that our small r is changing, right? Our Gaussian surface is getting larger, and as it gets larger, it chews up more and more of the spherical insulator, right? So we're slowly encompassing more and more of this enclosed charge. So let's take a look at what Q enclosed is. Okay, so Q enclosed is going to be equal to, well, it's going to be equal to it's basically going to be piecewise defined, right? It's going to be equal to different things when small r is less than big R. So there's going to be one definition when small r is less than or equal to big R, and then another one for when when small r is greater than R, right? So let's start off with when small r is less than or equal to R. We're going to end up with rho, our charge density, times the volume of our Gaussian surface, right? And if we just write in the expressions for that, we have them both up here. We have our density and we have our Vg here. We can just write both of those in. We're going to end up with, what was it? It's 3Q over 4 pi big R cubed. That's our density. And our volume is going to be 4/3, so it'll be 4 pi small r cubed over 3. Okay, and that's just substituting in for these two quantities. We can clean this up a bunch. These 3's are going to go, these 4's are going to go, these pi's are going to go, and we're just left with Q times this ratio. I'm just going to sort of factor out the power here, and we're left with R over R to the third. Okay, and this is the value of the enclosed charge as our small r approaches capital R. So for small r less than capital R, does this thing behave the way we would want it to? Well, it does, right? So let's say our r was 0. What would a small r of 0 mean? Well, that means that our Gaussian surface has no radius. It's super tiny and encloses no charge. So it's basically 0 times all of the charge, which is this Q. So we have no charge. That works fine. As our small r grows, we enclose more and more of the charge until our small r is equal to big R, and then this term becomes 1, and that's exactly what we want. The Q enclosed will be equal to all of the Q. This Q here is all of the charge on the insulating sphere, and so that's great. We got the result that we want to. And our small r can't get bigger than R here because we cut it off with this piecewise defined function, right? So let's take a look at what happens when our small r is larger than big R. Well, in that case, we end up with rho times, well, the total volume of our sphere, right? And we called that V tot before, so let's do it again. That's V total, And so what is this going to end up being? Well, I mean, we could substitute in numbers for this, but it's pretty simple to see what it's going to end up being. If we have the charge density times the total volume of our charge distribution, well, that's just going to be all the charge, right? So this is just going to be Q, right? So when small r is larger than r, we're enclosing all of the charge, okay? And that's Q enclosed for all the cases that we could think of. And now let's go back and use Gauss's law here. So Gauss's law, again, I'll rewrite it one more time, gives us our electric flux equal to the closed surface integral E dot dA equal to Q enclosed, which we just talked about, over epsilon naught. Okay, and again, we can take this integral, and because of the symmetry in the problem, the same way we did in the previous problem, we can see that this is going to become E dA, which is going to be able to be rewritten as E dA, right? And this is just EA, really, where A is the area of, well, the surface area of our enclosed Gaussian surface, right? And so this is going to end up being E 4 pi r squared, okay, small r squared, because this is our Gaussian surface as our Gaussian surface grows, right? And so this is great. We can just substitute this result back in for the integral and include the right-hand term, and so we end up with how much space do I have here? Yeah, I've got space. Okay, so we end up with E 4 pi r squared is equal to Q enclosed over epsilon naught, right? And so we just talked about how Q enclosed is piecewise defined, and so this result is going to be piecewise defined. We're going to find that for, I'll maybe separate this off. We'll find that for r less than or equal to big R, we have E equal to, and I'm just isolating E here by dividing through by our volume. We're going to find E is equal to Q enclosed over 4 pi r squared epsilon naught. But our Q enclosed for small r less than or equal to big R, we have up here, and that's just Q times small r over big R to the third. So we can substitute that in. That's going to end up being Q r over r cubed 4 pi r squared epsilon naught. And we can clean this up, right? Two of these small r's are going to cancel. We can move this big R into the basement, and this gives us our final result. E for, maybe I'll do this like this. I'll say E is equal to Q R over 4 pi epsilon naught big R cubed for r less than or equal to r. Okay, and that's our result when we're inside our insulating sphere, and when we're outside the insulating sphere, we have r small r greater than r, and this gives us E is equal to Q enclosed over 4 pi r squared epsilon naught, but we know that our Q enclosed here is just Q, right? And so this is just going to end up giving us, well, I can rewrite the final answer here, is going to give us E is equal to Q over 4 pi epsilon naught small r squared for r greater than big R. Okay, and those are our two results. If we go back up to the nice drawing that they provided for us, that's exactly what we see here. What do we see here? So for our radius of our Gaussian surface, for our small r approaching r, we get this increase that looks like this, right? Until our Gaussian surface hits the surface of the insulator, and then we're no longer picking up more charge, but our radius is increasing, so this thing starts to die off like r squared, right? We see 1 over r squared here, and so that's us sort of having a decreasing electric field as we get farther and farther from our charge distribution. And this is what it would look like, right? This is a piecewise defined function that we have over here, and those are the equations that give us the plot that we see above. Okay. In the next example, we are going to look at our infinitely charged rod again. So we already did this using Coulomb's law, and maybe this is an interesting point. Gauss's law and Coulomb's law both relate charge and electric field to each other, right? They're really equivalent ways of thinking about the same problem, but kind of coming at them somewhat differently, and depending on the symmetries of the problem, different ones can be easier. Well, either Gauss's law can be easier to use, or Coulomb's law, and depending on the problem, you're really going to want to select one or the other, and the symmetries will kind of guide you, and you'll get used to using them, so you'll see sort of which ones work in which situations. But really, the point is that they're equivalent ways of looking at the problem with different approaches, and so you have a couple of tools that you can use to try to take care of these problems. But before I get into this example, let me again pause and save so that we don't lose this. All right, let's get into this one. So what do we have here? We have an infinite rod, all right? So this rod will continue off in these directions. And again, there's no such thing as a charged infinite rod, but we can use this approximation when we're dealing with a very long rod and we're very close to it, right? Like let's say you had a very long wire, I don't know, 100-meter long wire, and you were like right up against it, a centimeter away from it. Well, the result for this problem would be very, very close to the result that we would find there, right? And so what do we have here? We have this electric charge distributed uniformly along the length of the wire. We have a charge per unit length, lambda, shown here. We assume it's positive, and so we want to find the electric field by using Gauss's law. Okay, and so they didn't label it here, but I'll put it in. We have lambda, and so we have some big Q distributed over well, we have to be careful here, right? Depending on how large we're talking about here, this Q would really be infinite if this thing extended infinitely. So maybe I won't even talk about Q. We're going to talk about enclosed Q afterward, but let's just talk about charge per unit length. We'll just talk about lambda for now, okay? Also, I'm going to want to label these surfaces because I'm going to talk about them individually. So basically what we have here is a closed cylindrical surface, right? But I'm going to talk about each part of these surfaces differently. I'm going to call this front face here, I'm going to call this S1. I'm going to call this drum-shaped part here S2. And this back face, this circular back face here, I'll call this S3. Okay. And so we're trying to find the electric field, and we can again make use of symmetries here, right? I'll talk about them as we go along, but for now let's keep in mind that symmetries are going to play an important part here in solving this problem. So start off from Gauss's law. That's usually where these are going to go. So we start off with Gauss's law. Gauss's law tells us that the electric flux is going to be equal to the surface integral E dot dA, which is equal to Q enclosed over epsilon naught again, okay? Let's take a look at this integral a little more closely. So we're focusing in on this integral. What does it mean to do the surface integral over this surface? This surface has three different parts, which I've labeled S1 through S3. So really what would we need to do? Well, there'd be different dAs, right? So there'd be a bunch of dAs that pointed in this direction here. There'd be a bunch of dAs that pointed in that direction, right? So like this would be some dA1 that would point in that direction. Our dA3s would point in that direction, right? And these dAs that are kind of pointing up here, they've written it sort of more generally as just a dA, but I mean these would also, we could think about these as dA2s, and they would always point sort of radially away from the wire as we go around our drum section here, right? So let's break up the integral. Basically, the integral is going to end up being so when I draw it like this, I mean for just this integral, or maybe I'll just rewrite it here. So the integral, which I've written like this, really we could break up into three parts, which would end up looking like this. We'd have some double integral over surface 1, which is this front face that we had here, of E dot dA, which I'll call dA1, which are all these tiny little dAs pointing off kind of to our left here, right? we would then have to add this to the surface integral over surface 2 of E dot dA2 plus the surface integral over surface 3 E dot dA3, right? Except that we can make some big simplifications here. First simplification that I'm going to make is that we can see that because of the symmetry of the problem, our electric field is always going to be pointing radially away from the wire, right? This is an infinite wire, so all contributions to the sort of left and right down the axis of this wire are going to cancel out, and all of our electric field is going to point radially away from the wire, right? And so what does that mean? Well, that means that as we do this dot product, all these dA1s and these dA3s are always going to be perpendicular to our electric field. And because of that, all of these are going to go to 0, and all of these are going to go to 0, right? And again, maybe I'll write it in here. This is because the electric field is perpendicular to dA1 in all cases. This is supposed to be like a perpendicular symbol, okay? And this one is as our electric field, again, is perpendicular to dA3 at all points. So both of these integrals go to 0. And what happens to this integral? Well, again, we don't have to worry about the dot product because of symmetry. Everywhere here, our dAs, our dA2s, are going to point in the same direction as our electric field points, right? They're all radially outward from the wire. And that's great. So that means that this integral is going to end up being, by symmetry, this integral is going to end up being the double integral over S2 of just E dA, right? But E is not going to change as we go around this thing, and so it's just going to flow through the integral. We're going to end up with this thing being equal to E times the double integral over the surface. This should be a dA2. And well, what is this? What is this double integral over the surface of dA2? Well, this is just the surface area of the surface that we're talking about. We're only integrating dA over that surface. That's always going to give us the surface area of the surface in question. So what is the area of the surface in question? Well, this is just going to be r, right? So we have the radius, so it's just going to be 2 pi r, which is going to give us the circumference, times L. So that's simple enough. So this just ends up being E times the area, and okay, maybe I'll write it in 2 steps. So it'll be E times the area, which is just E times 2 pi r, and they write there L like a lowercase l. I'll write it like a curly L. Okay, so maybe I'll put that in here so it's not confusing. Okay, so that's our area of the surface that we're integrating over. And then we just go right back to Gauss's law. We've cleaned up this seemingly messy integral. 2 parts of it canceled off to 0, or just went to 0 on their own. We were able to simplify the contribution from surface 2 down to this expression here. And so Gauss's law ends up giving us, do I have more space? I do. Maybe I'll write it down here. And so we end up getting the electric field times our area that we talked about before is equal to Q enclosed over epsilon naught, right? But what is our Q enclosed? We now want to find Q enclosed. Well, Q enclosed is just going to be equal to whatever our length that our surface covers, right? Times, because that's basically the length of the wire that we're covering, times the charge density in that wire, right? So that's just going to end up being lambda times L. And so I can just substitute that in there. We'll isolate for E, and so we end up with E is equal to, well, now lambda L over, we had an epsilon naught before, now we have a 2 pi r L. We can simplify this somewhat, and we end up with E is equal to lambda over 2 pi epsilon naught r. Okay, and we've seen this result before. This is the result that we saw before for the electric field outside of an infinite rod, and that's exactly what we find here, right? Exactly as we expect, and exactly as we found using Coulomb's law previously. Okay, so that's that example. And let's now do one last example. We're going to look at the electric field of a charged infinite plane here. But before I get into this one, let me save one more time before I lose all this. I will pause. Okay, and let's get into this final example here. Okay, so electric field outside of an infinite plane with some charge density sigma, right? So here's our infinite plane. Excuse me. And so they've only drawn a couple of electric field lines here. So we know that outside of this this plane, we're going to have our electric field looking like this on both sides, right? Okay. And again, I'm going to go through and label these surfaces. So again, I'm going to call this surface 1. I'll call the drum portion here surface 2, and this part over here, which we can't quite see, is surface 3. And so we know that there's some charge density, and because we're dealing with two dimensions here, this is signified by sigma, right? And so let's start off again. We start off with Gauss's law, and so we have excuse me. I'm going to stop writing or maybe I shouldn't. Well, okay, I will. So I'm going to stop writing the first term in Gauss's law, our electric flux. As I mentioned earlier, you're rarely actually calculating the electric flux itself. The electric flux is sort of a stepping stone between the electric field and the charge distribution, right? So we're rarely calculating our electric flux, and we're just looking for this relationship that I'm writing down here, right? So this is kind of how we want to think about Gauss's law. Okay, so this is from Gauss's law, and again, we just want to break up this integral. So we know that we can write this integral around the closed surface as the following. This is going to end up being the double integral over surface 1, E dot dA1, plus the double integral around surface 2, E dot dA2, plus the integral over surface 3, E dot dA3. Okay, but again, we can make some pretty significant simplifications here. So the first simplification that we're going to make is that while in the last case, if we look up here, our surface 1 and our surface 3 had their dAs perpendicular to E. That's the exact opposite of what's going on here. Here, our dA1 and our dA3 are perfectly parallel to the electric field at that point. Oh, and this line worries me. This caused a crash last time. We'll keep going with it and hope that it works out. Okay, so what does that mean? Well, this means that our surface 2 with its dAs pointing radially outward, this is going to be dA2, is always going to be perpendicular to E. So in this case, this thing goes to 0 because dA2 is perpendicular to E. Okay, and we can also make a simplification here in that whatever our result for surface 1 is, that's going to be exactly the same as our result for surface 3, right? It's going to be the same magnitude of E, assuming that we're the same distance, which we would be by our setup here. So we're going to end up with the same magnitude and the same direction for our electric field at everywhere on that point, and obviously our area vectors are going to be the same also, because this thing is a cylinder and it has the same sort of circular caps on each side, right? So we can just combine this and this. So we just combine these, and we just end up with let's say twice the first one, right? So we're going to end up with the expression that I'm going to write down over here. And so this is telling us that this integral, which we started with above, is actually just going to end up being 2 twice the integral S1. And I'm going to make another simplification because we know that E for these regions points in the same direction as dA, right? We know that our dA ones are going to point in that direction. So E dot dA is just going to be the same as E multiplied by dA. So this is going to be E dA1, and that's really our whole integral. This 2 comes from the fact that I'm counting twice, right? This is over surface 1 and surface 3, which we argued would be the same, and so we have this factor of 2. But obviously we can just clean this up a little bit. Let's say, or let's instead of cleaning it up, no, okay, I'll clean it up one step and then we'll go from there. So this is going to be 2e surface integral 1 dA1. And again, like we said before, because we're integrating dA over the surface that makes up these dAs, we just end up with our area vector, right? Or with our area, I should say. And so we just end up with 2EA, okay? Substituting this back into our original equation up here, into our Gauss's law, we're going to find that we have 2EA is equal to Q enclosed, over epsilon naught, right? And we're looking for E, but before we're able to get there, we need to talk a little bit about what Q enclosed is. What is Q enclosed here? Well, Q enclosed is going to be equal to our charge density, right? So our sigma, which is over the full surface, times the area that we're enclosing, right? Times the area of this circular region, right? So that's just going to end up being sigma times the A, right? Because A that we have here is the area of one of these circles, but that's the same area as we're enclosing on the surface, right? We can imagine that this is just the surface here, and this is the amount of charge that we're enclosing, right? So that Q enclosed is going to end up being sigma A. And so we can make that substitution. I won't add another page in here. We're basically there. This is going to mean that 2EA is equal to sigma A over epsilon naught. And I can just cancel off these A's, move this 2 over, and this gives us our final answer. E has a magnitude of sigma over 2 epsilon naught, right? And this is the result that we found for the electric field outside of an infinite plane with a charge density of sigma, right? Same result that we found in the case of Coulomb's law. Okay, so we just saw a number of applications of Gauss's law here, and we're going to look at some more stuff in the next video. But for now, we'll leave it here with these examples. I'll see you guys in the next one.